So you remember back in general physics when we started with kinematics and then we did forces and then we got to the really cool stuff like energy. And what was really neat about energy was I didn't necessarily have to worry about my vectors and keeping track of my vectors because we could work in a scalar product kind of an idea. So here in chapter 14, what we're doing is we're going to bring in work and energy into our dynamics equations. So far what we've done is we've done our kinematics equations and we've expanded that to where we can do them in polar coordinates and in cylindrical coordinates, and we can utilize those coordinate systems to really help us out. And that gave us more complex problems than what we got back in engineering physics. So then we moved on to forces and looked at those forces. And because we had dealt with velocity and acceleration, and we dealt with acceleration, both the tangential and radial components, or normal and tangential components, we could actually do a lot more complex problems than what we encountered back in engineering physics. Similarly here, we're going to take it in the next step and we're going to actually look at it in terms of work and energy. So recall that work was that dot product between force and distance. And we can look at the force will do work on any particle only on the particle as it undergoes a displacement in the direction of the force. Remember that we had to deal with that angle coordinate. And so now as we're traveling along any path, we're going to have to look at the force along that path. And we're going to use our change in R as our dr. And so work is like an energy function, and energy has the capacity to do work. So we're going to look at our change in energy, which is equal to the work, times our scalar product. And now we're going to get an equation that we're going to expand upon what we did back in engineering physics. So let's look at how the author kind of presents this material. So work is defined as the force, as the product of the force and the displacement components acting in the same direction. That dot product, that dot product, which gives us that cosine of the angle. And so we can get that change in our energy, just like what we saw on that first page. By using that definition of the dot product and integrating, we can put in our force cosine theta and we can get that total energy. And so now we're looking at the force that's along that portion of our path that we're keeping track of. Also remember that when we were dealing with forces, we're going to introduce variable forces, which is what's making it a little bit more complicated, and work is related to the area under the curve. So we still have our same energy equation, and if force is a constant, we get that same type of an equation that we saw in our engineering physics. So again, we're going to be able to deal with a variable force, whereas in engineering physics, we've kind of kept it simple and looked only at a constant. So now we can look at the work done by gravity. It gives us a good example that we have gravity coming down. We remember that our work is related to weight, and we can have our negative work times the change in the height. And if I look at this as along a particle, here is my change in my path as related to the I, Y, and Z directions. And we recall that the scalar product of I dot I, J dot J, K dot K is equal to 1, and any other iteration is going to equal to 0. We can look at this in terms of our dot product, and we're going to end up in the same type of an equation as what we get by looking at it from that perspective. So the work of the weight is the product of the magnitude's particle weight and its vertical displacement. And again, that comes from these dot products here, that I have to be in that same direction as the work, or as the path is being moved. So we want to expand it because not only did we deal with gravitational potential energy, we also dealt with springs. So we want to look at the same situation dealing with an elastic spring. And remember, we had that the magnitude of the force was related to our spring constant times the displacement from the unstretched spring. remember we're looking at the stretch. And if we were looking at Hooke's law, remember that it's a restoring force. We can do that same type of an evaluation using our integration, and we're going to get the 1/2 ks squared, just like what we had seen before. So nothing new here, except we're introducing the fact that we can have a variable force. So the next part is we want to kind of look at this and look at how this works out in terms of our work energy theorem. A couple things that I need to point out. We can integrate our equations of motion, and we can look at this in terms of our tangential motion and our mass times acceleration. And we can rewrite our mass times acceleration in here, which is going to give us our change in kinetic energy, 1/2 mv squared. And we can relate that back to our work energy theorem. We're going to use T as kinetic energies, and U is the work done by all the forces. And so we're going to have that same kind of notation issue that we saw early on when you would open up any other engineering physics book. When you open up other mechanics books, whether it's a physics mechanics book or a dynamics book in engineering, you're going to see that each author may make a little bit of a change in terms of its terminology, and we're going to use T. The big things we got to remember out of this is it's not a vector equation. Because we're doing this, we're using the scalar, we're using the dot product, we can get rid of that vector notation. We also want to know that our units are in joules and they're in foot-pounds if we're in the English system. So we're dealing with those energies. And the principle of work and energy cannot be used to determine forces directed normal to the path. This is one of the places that we're making that change, that when we're doing work, we're doing that work along the path of the motion, and work isn't being done in that other dimension. So if I'm pushing that grocery cart down the aisle, I'm only interested in the force that's allowing me to push it horizontally. Anything else I'm doing has the potential to be wasted. Or worse, if I'm pushing down a little bit more, it's going to increase friction with the surface, and I'm going to lose energy as a result of that. So we can look at it as a system of particles. So as we move on in this chapter, we're also going to look at power and efficiency. Remember that power is defined as the amount of work performed over a unit time. So when we're doing that work, it's that change in work with respect to time. Remember that work is going to be a scalar, and we can actually look at power in terms of the dot product of the force, dot product with velocity. So power is a scalar function, and it's a product of force and velocity. But again, those components have to be in the same direction. I dot I is equal to 1. J dot J is equal to 1, K dot K is equal to 1, and those are our unit vectors in the same direction. And that's really important as we work these problems. Also, so we can look at our power function, because again, we're dealing with that scalar. So the velocity of a body acted on by a force is known. The power can be determined by calculating that dot product. Our units of power are watts, which is a joule per second. Or if we're in our traditional English system, it's 1 horsepower, which is 55 foot-pounds per second, or 746 watts. So going back to that conversion factor. Now we're in dynamics and we're in engineering, so we want to look at mechanical efficiency. So we want to do, and that's a machine value that we're looking at it, and it's a ratio of the useful power supplied, the output power, to the power supplied to the useful power, the output power to the power supplied to the machine, or the input power. And that's going to give me that efficiency ratio. If the energy input and removal are at the same time, the efficiency may be also represented as the ratio of the output energy to the input energy. And machines always have frictional forces, so we're always overcoming it. And since frictional forces dissipate energy, our efficiency of machines is always less than 1. All right. And it comes in because I am going to lose energy. It goes back to that second law of thermodynamics, which means that I can't break even. Mother Nature's a pain and I can't break even. So procedures for working these problems is very similar to what we've seen before. We've got to define the external forces acting on the body. We have to draw those free body diagrams. We need to determine our velocities at the point at which the force is being applied. We need to look at the force magnitude and the velocity of the direction to the force so we can get our power, and we can calculate power by changing the work, and we can get that mechanical efficiency. So this is more for when we start getting into those power equations and those efficiency equations. So what I'm going to do now is I'm going to do two examples as part of this presentation, and then I'm going to give you a bunch of other examples to look at. And those are going to be separate, and I think that's going to be a little bit better for us to handle so that you can look at the individual problems. So let's take this first one. So what we've got is we're given a system here that we're going to use this winch to bring up our weight. And we're told that the motor is going to bring it up with a force of 600 plus 2 times the distance squared in newtons. And we want to determine the velocity when this reaches a height of 15 meters. And our initial velocity is equal to 0. So we got to use our force diagrams to come up. And because of the way this system is with a pulley, we're going to have 2 times the tension minus the weight of our object is going to equal the mass times acceleration, which is going to equal the force. Now the work is just going to be our change in kinetic energy. The work is also our dot product. So what we're going to end up dealing with is I've got to figure out what this tension is, and that relates back to this. And then I've got negative of this is my work portion. This is my potential energy portion, and it's going to equal 1/2 mv squared. So it's the work that being done on the mass. The height is going to equal my change in kinetic energy. We can plug this in and evaluate from 0 to 15. And we can get our equation here, and that's going to give me that once I plug in for the 15 for S, I'm going to show that the velocity is equal to 12.5 meters per second. So we start doing those same kinds of problems that we saw back in engineering physics, except now we can bring in the fact that we have a variable force. The force isn't necessarily constant. So let's do another simple problem, very simple to what we've had before. I've got a box that's being dragged across the floor. It has a coefficient of static friction that I've got to overcome. That's going to equal 0.2 times our force due to friction. It's going to have a weight, which is going to be 100 kilograms times the 9.8. And I have these two forces that are being applied. This is problem 14-4, so I'm going to read it for you. That we have a 100 kilogram crate that is subject to the forces shown. If it's originally at rest, so we're going to have to overcome that static friction and determine the distance it slides in order to maintain a speed of 8 meters per second. The coefficient of kinetic friction between the crate and the surface is equal to 0.2. So I'm sorry, I actually have it written wrong down here. This should be the coefficient of kinetic friction, and this should be the coefficient of kinetic friction, but the process is going to work, and we want to find our change in distance. So the first thing I've got to know is how much is that force due to friction? Okay, the force due to friction is where I have to deal with, and I have left off an S here. This should be an S in this particular spot, because when I do the work due to friction, this is 165.49 S, right? That change in distance. And when you do all of that, you're going to get the 534.47 times my change in distance. So what's going to happen here is I've got the work that's provided by force 1, the work that's provided by force 2, and I have to overcome the work that I'm having to fight friction with. And that's going to equal my change in kinetic energy. And this is only going to be related to the final because my initial kinetic energy starts at 0. So once we plug all of this in, we're going to get an equation that looks like this. And we're going to find that the distance traveled is 5.99 meters, or approximately 6 meters. Now I'm going to start populating with some sample problems for this chapter, but this gives you the overall basic theory that we have been dealing with, or we dealt with back in engineering physics. And so now you can start to see how each one of these classes build on itself, and we can utilize them there. But this should get you started with our chapter 14 type homework.